Welcome to this video. This is video number 3 in my series of videos on Whitehead and Russell's Principia Mathematica. In this video, I'm going to go through sections 2 to section 5 from the first edition of Principia Mathematica. And in these sections, what we're going to see are some propositions which are, in a way, immediate consequences of the primitive propositions which I introduced in the previous video, in video number 2 from this series. As you might expect, some of the propositions in these sections are fairly elementary in nature. Some of them are useful at later stages. They're used extensively throughout the rest of the work. Some of them are interesting in themselves, in their own right, and other propositions might be included more for sake of completeness. So if you've got a family of a few propositions, and there's another proposition which kind of belongs to that family of propositions, then it will usually be included, even if it's not something that necessarily gets used further down the line. What we're really interested in at this stage is just getting some kind of familiarity with the style of the notation, the style of presentation, and the style of delivery of the propositions and the demonstrations and things like that in Principia Mathematica. So it is worth at this stage going through things fairly carefully just to make sure that you've got a good level of familiarity. The demonstrations in these sections tend to be a bit more detailed than they will be further down the line. I'm going to be concentrating on a few propositions which really illustrate well these notational and presentational aspects that I think are important to really understanding Principia Mathematica. So yes, I will go through some propositions and the demonstrations of those propositions which are important in themselves, but just because I go through a proposition or its demonstration doesn't necessarily mean that the proposition itself is important. It might be some kind of notational aspects that I'm wanting to highlight or something similar. As with any book on logic, things will start out with very strict proofs, set out in a very strict and detailed way, but eventually this gives way to a much more relaxed approach. Principia Mathematica is no exception to this. It's tempting to think, if you casually flip through Principia Mathematica, that it's incredibly detailed. And it is detailed to a certain extent, but it's also surprisingly casual in its approach once you get beyond a certain point. And it has to be like this, because if everything was written out in the most minute detail, then Principia Mathematica would be, I'd imagine, 10, 20 times longer, if not more, than it actually is. So to bring things down to at least a manageable kind of level, some things have to be omitted, some things have to be a bit more dealt with in a bit more casual manner. As with just about any book on logic, Principia Mathematica starts out with very strict proofs, set out in a very strict and detailed way, but soon this gives way to a much more relaxed approach. It's tempting to think that Principia Mathematica goes through everything in minute detail, and it's very easy to get this impression if you casually flip through Principia Mathematica. But just to be clear, it doesn't go into the minute detail that you might think and expect. In fact, it's surprisingly casual beyond a certain point. It doesn't go into the minute detail because, like any other book really, it can't. First of all, the book is meant to be read and it's meant to be understood. And if everything was written out in full comprehensive detail, then the increase in detail, the gain in detail, would soon be lost in incomprehensibility. It would be completely impossible for any normal human being to understand it, and it would be completely uninformative as well. However, Principia Mathematica does give a very good idea about how things, at least in theory, could be reduced to a purely symbolic, logical form, but without actually necessarily going all the way to doing that. So a great number of propositions are not even proved explicitly in Principia Mathematica, with just citations given as to which of the previous propositions might be used to demonstrate the current proposition. You'll find that in the demonstrations of certain propositions in Principia Mathematica, references and citations to earlier propositions that are being used to make certain inferences in the demonstration of the current proposition. In the earlier stages, these citations and references will be fairly consistently and comprehensively identified, but later, however, you'll find that only the main propositions or the more unusual propositions are identified, and there are other propositions that are being used, but they're either obvious or you've just got to figure them out for yourself. They're not explicitly mentioned. And again, really this has to be the case, otherwise we end up in the situation where we've just got masses and masses and masses of symbols, citations, references, and it just becomes completely incomprehensible, and any gain in detail in that respect is quickly lost in incomprehensibility. It'd be completely impractical to do so, and no one would ultimately be able to understand what's going on. So really it's done, this more casual approach is done really for reasons of comprehension more than anything. It is worth it, however, in the earlier stages to have a fairly strict mindset about how you go about things and trying to identify all of the propositions that are used in a particular inference, as much as possible at least, but not necessarily worrying so much about it if you do have to relent a little bit, and have to take a slightly more relaxed approach to things, certainly later on anyway. It certainly won't be possible for me to go through all of the propositions and demonstrations from section 2 to section 5. That's not the aim of these videos, really. What I really do want to do is to just take the time to go through a couple of demonstrations in a bit more detail, just to see how things are working, but many of the propositions towards the end of section 2 are very similar to one another, so much so that the demonstration's not even given in full in Principia Mathematica, and only the propositions that you're really going to need to write out the proofs yourself are actually cited. It is worth, to a certain extent, if you are reading Principia Mathematica yourself, to have a go at writing out some of these propositions, just so you get a better feel for the notation and style of presentation and things like that. You don't have to do this, but it does help. I've done it a few times myself, and it's helped me just understand things a little bit clearer. Another reason to have quite a strict mindset, at least in the earlier stages of reading Principia Mathematica, is to convince yourself that nothing is entering the reasoning, the chains of reasoning that is unjustified. This is particularly easy to do if you're doing something that's of a particularly elementary nature. Then sometimes you can think through it so quickly that you're thinking more unconsciously, subconsciously, I don't know which one it is, than consciously. So there are certain processes that are going on that are just so automatic that you don't even consciously register them. And what we've got to try to do, maybe in the earlier stages, is just check our thinking a little bit, slow things down, analyze what we're doing step by step as much as possible, just to satisfy ourselves that nothing unjustified is going on, or if there is anything that we feel is unjustified, that we try to address that issue. Obviously we can't necessarily be 100% certain about this, but it's something that we should really be watching out for. So most of this video is going to be spent going through some demonstrations of propositions from section 2, because this is where everything is brand new, effectively. All of the notation, all of the style of presentation, how demonstrations are going to be set out. This is where we're really finding our feet. Once we get past section 2, there's not a great deal for me to say about sections 3, 4 and 5, other than a few definitions. There are a few comments that I need to make, a few interesting propositions, but in terms of notation, there's nothing really new introduced in these particular sections. So once we get onto these sections, there's just a few things that I need to mention, but nothing special really. Anyone who's got any basic familiarity with propositional logic will find absolutely no surprises, nothing out of the ordinary with the propositions in these sections. So on that note, let's get started. This is the first proposition that I'm going to go through in this video then, the first non-primitive proposition. It's actually the first non-primitive proposition that's introduced in Principia Mathematica. So what that means is that this proposition actually has its own demonstration. So this is the first proposition that's actually proved, demonstrated in Principia Mathematica. So the number of this is 2.01. Let's just have a look at what this proposition says. So it simply says that it can be asserted that if P implies not P, this in turn implies not P. So if a proposition implies its negation, this implies that the negation is true. So this proposition has a name. It's got its own name. It's called the Principle of Reductio ad absurdum. ABS is going to be the abbreviation that we use if we want to refer to this particular proposition. So Reductio ad absurdum, as you might already know, is the kind of the principle used when you want to prove something like the textbook example is when you want to prove that the square root of 2 is irrational. You typically use a reductio ad absurdum. I'm sure there's lots of different ways that you can prove square root of 2, but the most common one is using a reductio ad absurdum. Just to clarify what the dot notation's doing here, I'm just going to write it out again and just clarify the dot notation for anybody that's struggling with that. So, as I said in I think it was the last video, what you're looking for with the dot notation, you want to identify which dots represent logical products, which dots represent brackets. Well, we don't have a logical product yet. We've not defined it, we've not introduced it. So all of these dots here are going to represent brackets. So we've got a single dot here, a single dot here, and 2 dots here. So the idea is that a greater number of dots, which represents brackets, will extend over a smaller number of dots. So here we've got 2 dots. So we're going to get a bracket that opens up here. This is the beginning of the proposition, and it's going to extend all the way over this dot, and until, in fact, we get to the end here. Now, what would in general happen is that the brackets would extend until you get to a greater number of dots, at which point you would close off your bracket, as we're going to see in a second. So if we take this single dot here, so we put one of the parentheses there, and we don't want to extend over the implication symbol. We kind of go away, the brackets go away from any logical constants. So whether this was implication or disjunction or whatever equivalence, we tend to open the brackets in a way that is going to cause the brackets to go away, loosely speaking, from the logical constant. And this bracket, the other side of this bracket, we're going to go as far as we can, but we've got to stop here because, we've got 2 dots here. The 1 dot is, this takes priority. The 2 dots takes priority over the 1 dot, so it doesn't allow me to extend any further than that, so I close my bracket there. Similarly over here, I've got the 1 dot here, open up my bracket, again away from the implication symbol, and I extend as far as I can. In fact, in this case, I actually come to the end of the expression itself. I don't come to a greater number of dots. So I just draw, close my brackets at the end of the expression here. So what we see then is that P implies not P, all belongs together, and it's that implies not P. So let's have a look at the demonstration now of this particular proposition. So dem for demonstration, obviously. And what we see here is we've got an assertion, and we've got some square brackets with something written inside. And what this is indicating is that this assertion is being made in accordance with whatever rule or proposition or propositions is or are being quoted or cited in these square brackets here. So they're not formally part of the demonstration, they're just to give you a bit of an idea about where this assertion originates from, how you can be sure that this assertion comes about. And okay, so the taut, that's referring to primitive proposition 1.2. If you remember from the last video, proposition 1.2 actually has its own name, which is the principle of tautology, and taut is the abbreviation that we use to refer to that particular primitive proposition. I could quite easily have written star 1.2 instead of taut in here, but typically if you've got a proposition that also has a name, which usually means that the proposition is it's important in some way, it's going to be used quite often, or it's a particularly important principle, then you will usually refer to its name rather than its number. Although further down the line we will see that there are certain propositions that don't have names, and we refer to them by their number within Principia Mathematica. And what this is saying is that we're using primitive proposition 1.2 with the P of that proposition replaced with not P. So this is what the symbol was in the original statement of star 1.2, proposition 1.2, principle of tautology, and this is what we're replacing it with. And it's important to understand that whatever proposition that we have, we can always make substitutions, appropriate substitutions in those propositions, usually with other propositions or with the propositional functions, for instance, and the thing still remains true. So it's really the form of the proposition that we're interested in. So if we just write out what star 1.2 is, it says that P or P implies P. Okay, so the disjunction of P with itself implies P. Well, what we've done here then is we've taken out the P's and replaced them with not P. Now I've got to replace all of the P's. I can't just replace some of them, I've got to replace all of them to keep the same form, because if I only replaced this one, let's say I wrote something like that, well, that's not the same form, that's a completely different thing. In fact, it's probably not even true, so I'm going to put some exclamation marks around that because it's not necessarily even true. So I've made the error here of only substituting one of the P's with not P. If I'm going to replace P with not P, I've got to replace all of the P's with not P. But similarly, I could replace with more complicated expressions. So I could write something like, replace the P with P or Q. So P or Q, or P or Q implies P or Q, for instance. It's still got the same form. A proposition, the disjunction of a proposition with itself implies the proposition. So all of these are effectively immediate consequences of this star 1.2, just with different substitutions being made. So what we're highlighting here is that we're not just using principle 1.2, there is a change that has been made to it. Now this, after a few pages of Principia Mathematica, we will stop doing this. Whitehead and Russell stop doing this. They expect you to start seeing yourself. They'll still quote, in a lot of cases, the proposition that's being used, but they will suppress this information here. You'll have to figure out yourself exactly what has been substituted for what. Sometimes it's easy, sometimes it's a little bit tricky to do, but you won't be given this leg up. And then other times, even further on, you might even not be told exactly which propositions. As I've already mentioned earlier in this video, you will be given the main propositions as citations, and then the other ones you've got to figure out for yourself. Okay, so we can assert this by use of this particular proposition, primitive proposition, and we're going to call it 1. So this is not indicating that this is the first line, it's just indicating that we're calling this 1, because we're going to want to refer to this in the next line, and we don't really want to have to write it all out. So we don't necessarily number all of the lines, we just number the lines that we anticipate we're going to need to refer to later on. So sometimes there will be lines that don't have any numbers at all that appear, and that's usually because they're not used in any subsequent parts once the current bit is finished, really. So that's the first line done, and then we're on to the second line. And again, we've got an assertion, and we've got a box full of information here, square brackets with some information inside. So the information that these square brackets contains will vary, but it's usually just giving you hints as to what information is where this assertion has come from. So what this is saying is that we're using the line that we've labelled 1, and we are somehow, we've got to a certain extent, figure out how this star 1.01 is being applied to that. Now I can see that this is a definition here, because the number of the proposition is actually in brackets, so it's not a proposition at all, it's actually a definition. If we go back to this one here, if I'd written this using the star 1.2, I wouldn't have put curly brackets, or parentheses, sorry, around it. I would have just written this. So the brackets here around the star 1.01 indicate that this is a definition that's being used here. And what is this a definition of? It's the definition of implication. So the definition of implication is that P implies Q is defined to be not P or Q. So again, we're looking at the form here. We've got to figure out how has this been applied to it. Well, it's here because this is where the disjunction changes from disjunction to implication. And if you look here at the pattern that that this definition gives, and I've missed a little bit off there, it should be like that. The only difference really is, well, obviously the disjunction in the implication symbol, the Q stays the same, but the not P here was P in the implication, or it should be P in the implication. So the not P here changes to P. This not P stays the same. Again, remember it's the form that we're interested in, so we've effectively substituted Q for not P in our expression here. And if we make the appropriate substitution of the implication, we get this. And that gives, that's the end of our demonstration. So this demonstration, this proposition is so simple to prove that we didn't even need to use our rules of inference. It's so straightforward to prove. So here we come to the second proposition that I'm going to, whose demonstration I'm going to go through in this video. But the comments that I'm going to make regarding this are going to be less thorough than the last proposition, because the form of the demonstration and everything is pretty much the same. But I want to go through this one because it is an important proposition that's going to be used quite extensively, this and the next proposition that I'm going to introduce. So this is star 2.05, and it also has its own name, which is the Principle of Syllogism. Confusingly, this and the next proposition that I go through are both referred to as the Principle of Syllogism. There is a difference between the two, and which one is being used when it's referred to as just Syl. In that respect can be a little bit ambiguous, and you've got to figure it out for yourself which one exactly is being used. So you might think it would be better to refer to the numbers, but it's not. So, okay, this says that it can be asserted that if Q implies R, this implies that if P implies Q, this implies P implies R. Okay, so again, I'm just going to clarify the brackets. So if I just quickly write this out here. Mr. Dot. Okay, so again, all of the dots refer to brackets in this particular proposition. We don't have any logical products yet. So the three dots here are going to open up there, and they're going to extend over this single dot, these double dots here, this single dot, this single dot. They're going to go right to the end of the expression, which is what we'd expect. The dots immediately following the assertion symbol, we would expect to pass right over to cover the whole proposition, effectively. Okay, so then I've got this single dot here. We don't want it to go that way. We want the brackets to go this way, effectively. So I go as far as the three dots here. Remember, because this is one dot, I go as far effectively as I can until I meet a point where I've got a greater number of dots. Which here I've got 3 dots, so I can't go any further than that. So this dot here brackets off the Q implies R. Over here, the single dot here brackets off the P implies R. This single dot again extends this way away from the implication symbol, and it will extend as far as these 2 dots here, at which case it'll be closed. And then the 2 dots here are going to extend again in that direction away from the implication symbol, and they're going to go over this single dot, over this single dot here, and I'm going to close in there. So I'm not necessarily saying that the order that I've done everything there is some ideal order. You've just got to find your own way of dealing with the brackets, or ideally with the dots, to be honest with you. But eventually it becomes quite intuitive what belongs where. Okay, so looking at the demonstration of this particular proposition, we've got, again, the square brackets before the assertion symbol, which is indicating that this assertion here is being made in accordance with whatever's inside this. The hints really come from inside these square brackets. So it's the primitive proposition that we referred to as sum, which I think was primitive proposition 1.6, if I remember rightly. And with the exception, again, concentrating on the form, with the exception that wherever we saw P in that particular proposition, it is now replaced with not P. So in the original star 1.6, we would have had something like, presumably Q implies R implies P or Q implies P or R, I imagine then. So the substitution that's been made is that this P and this P, remember, if we replace P somewhere, we've got to replace all of them with the same thing in order to keep the same form there. This P and this P have both been replaced with the not P, as indicated by this here. That again we're going to call 1, not necessarily because it's the first line. In fact, we'll see further down the line that what we call 1 sometimes won't be the first line of the demonstration. It's just what we decide to call 1. And then moving on to the next line, we've got another assertion here which is made in accordance with whatever's written in these square brackets here. So this is saying that definition 1.01, again indicating that it's a definition by the round brackets, curly brackets, parentheses, I don't know what they're called exactly, but that definition is being applied to whatever we've called 1. Again, we've got to figure out sometimes exactly how that definition is being applied, or how such and such a proposition is being used. Whatever's in these square brackets is not intended to be fully comprehensive in all respects. It's just meant to give some hints. Sometimes the hint is more obvious than other times, but ultimately we might have to do a little bit of legwork ourselves. So this definition 1.01 evidently has been applied to this and this here, and we get the P implies Q and the P implies R, which gives the final form of the proposition that we wanted to prove in the first place. Okay, so let's have a look at this proposition, which is 2.06. This is, in my opinion, the first proposition in Principia Mathematica with some real substance to it. It's not that the propositions 2.01 to 2.05 are not important, that they're not useful. They certainly are. It's just that we haven't actually really proved anything using any of our rules of inference yet. We've found that these propositions 2.01 to 05 are effectively just instances of the primitive propositions with a couple of tweaks here and there. Change a symbol here, change a symbol there, and we get a new proposition, but effectively it's a primitive proposition in a slightly different guise. Here we're actually going to have to make an actual inference, as we're going to see in this last line here. This proposition has its own name, the principle of syllogism, like the previous proposition as well, 2.05, which is also referred to as the principle of syllogism. So anybody that's got any familiarity with syllogistic reasoning might expect something more along the lines of P implies Q and Q implies R implies P implies R. And this is admittedly that is a better form of the syllogism, but the problem that we have at this moment in time is that we don't have a notion of logical product. It's not been defined yet. We still want to make use of syllogistic inferences though. We still want to be able to use something like this to help us make inferences further down the line. So this is the best that we can do for now. In the next section, in section 3, we will introduce more convenient and more usual forms of the syllogism. But for the time being, we're going to have to make do with this and 2.05 as well. What we're going to find is that 2.05 and 2.06 are going to become rules of inference for us. Whereas we introduced in the last video our basic rules of inference, 1.1 and 1.11. They are very basic, primitive rules of inference. They get the job done, but to make more complex inferences in more complicated chains of reasoning, we find that they're a bit kind of inadequate, practically speaking. Not theoretically speaking, but practically speaking. And that's where this is going to come in. So in a short while, not immediately, but in a short while, we're going to show how 2.05 and 2.06 can be implemented as rules of inference to make much more complicated inferences in a much shorter space of time and with much less complexity in the demonstrations as well. So let's have a look at this, the demonstration of this particular proposition. Just before I get stuck into the demonstration, let me just explain the dot notation, how it's working here. I'm not going to write the whole thing out again, I'm just going to simply explain what's going on briefly. So, okay, we've got all of the dots represent brackets, none represent logical products, because again we don't have logical products yet. The single dot here is going to extend in this direction, again away from the implication symbol, the logical constant, and it's going to extend as far as these 3 dots here, at which point it has to stop because it's reached a greater number of dots. So the single dot here brackets off the P implies Q. Similarly, the single dot here is going to extend back this way until it gets to these 2 dots here, at which point it has to stop. So this dot, it brackets off the Q implies R. This dot extends to the end of the expression to bracket off P implies R. The 2 dots here are going to extend over the single dots here. I'm going to pass straight over, and it's going to extend to the end of the expression and bracket off the Q implies R implies P implies R. And then the 3 dots here are going to bracket off the whole proposition, which is what we'd expect. The dots straight after the assertion symbol, we would expect to bracket off the whole of the proposition that we're wanting to prove. Okay, so now onto the demonstration. So the first line of the demonstration here is a particularly long assertion, and I've put some boxes around here. These are going to become clear in a second. I've just split everything up in a particular way that will become clear in a short while. But this is all one line here. This is the main implication, and all of these are kind of subordinate implications, but this is the main implication, and this is something that we're going to need to focus on in a short while. So what this is saying is that this assertion is being made in accordance with the principle of commutativity, with these appropriate substitutions. So this is proposition 2.04, which I've not stated, and I've not gone through the demonstration of it, but I think it's 2.04. If you want to know what it is, then either you can look it up yourself in your copy of Principia Mathematica, or you can kind of work backwards, just reverse the substitutions that I've made here, and you'll get whatever that particular proposition is. But making the appropriate substitutions, we get something that looks like this. Remember, all of this is one single line, and we're going to call it 1. We're going to label it 1. The next line is effectively just a straightforward assertion of star 2.05. So the previous proposition that I looked at, it's that one without any changes whatsoever. It's just exactly as it appears in the statements of the original proposition, and we're going to label that 2. Now, the reason I've put these boxes around here, these two in green and this one in red, is because this is identical to this. Now, this is effectively the hypothesis of this implication. This is the main implication in this proposition, and this is its hypothesis, and this is its consequence. And it turns out that we are asserting an implication, and we are asserting its hypothesis. So that's going to lead us to use our one of our rules of inference, okay? And that's what's indicated here. So what this is saying in the little box here is that this assertion is being made in accordance with an application of our rule of inference 1.11 to the lines 1 and 2. Okay, so I'll explain why we're using star 1.11 and not 1.1 in a second, but suffice it to say that even though we've got two rules of inference, 1.1 and 1.11, 1.1 is the more fundamental of the two rules of inference that we've got currently. But it's not necessarily the most useful because it applies really only to individual propositions. So if I've got something like P is asserted and P implies Q is asserted, then I can assert Q. But seldom will we actually work with individual propositions like this. We might do from time to time, but not very often. What we're more likely to come across are propositional functions, and that's what these are. Propositional functions. We can see them as propositional functions. Well, the form in that case that we're interested in is that if the propositional function phi x is asserted and phi x implies psi x is asserted, then we can assert psi x, where x is a real variable. Well, the beauty of this this primitive proposition, this star 1.11, our rule of inference applied to propositional functions, is that it applies to propositional functions whose arguments are propositions, not just more abstract things, individuals that we're going to come to further down the line. So we could reformulate this in terms of propositional functions whose arguments are indeed propositions, but moreover, we can extend it even further to propositional functions which have several arguments. So it's still got to be a finite number, but any finite number of arguments which are propositional elementary propositions, sorry. So I can reformulate this even further to something like PQR implies psi PQR psi PQR. Well, this is perfect, because now if I call this my phi PQR and I call this my psi PQR, then I've got exactly something of this form, which indicates why it's appropriate for me to use this primitive proposition, this rule of inference star 1.11, as opposed to 1.1. So that brings us to the end of this, the demonstration of this particular proposition. So I'm going to move on now to the next proposition. The next proposition that I want to go through is 2.11, which is the so-called Principle of Excluded Middle, which states that it can be asserted that P or not P. In other words, either P is true or its negation, not P, is true. Philosophically, this is an extremely important proposition. As innocuous as it may appear to be, and as uncontroversial as it may appear to be, it does suggest that we've got to make quite a substantial commitment within our system. The commitment that we have to make now, in light of this proposition, is that we accept that any proposition is either true or its negation is true. Which might seem obvious, that if something's not true, then it must be false, and if something's not false, then it must be true. But things are not quite so straightforward, at least from a philosophical standpoint. And at the time of writing of Principia Mathematica, this particular principle, the law of excluded middle, was starting to come under some heavy criticism, and certain schools of thought, certain philosophies of mathematics and logic started to reject the law of excluded middle, because what this effectively says is that any proposition, whether we know it or not, must either be true or false. So we can't have anything like indeterminate propositions, or propositions that are neither true nor false, which might seem fairly uncontroversial, but it is possible within certain philosophies that propositions that haven't been proved true or false are indeterminate or something, but they can't. It can't be assumed that they have a definite truth value within the system. But that's kind of beside the point to a certain extent. We're interested in the system that we are developing here, which is this logical system of mathematics, and this is one of the results that obtains in that system, and therefore we have to effectively go along with whatever this proposition says, which means that we accept that any proposition within our system is either true or its negation is true, even if we don't necessarily know the truth value of a particular proposition objectively. It will still have a truth value within our system according to this particular proposition. So let's have a look at the demonstration then. It's a fairly short demonstration, there's not really much to it, a two-liner. The first line, it can be asserted that not P or P implies P or not P. Just to clarify here with the dot notation, the single dot here is bracketing off the not P or P, the single dot here is bracketing off the P or not P, and the two dots here are bracketing off the whole of the proposition. So this assertion is being made in line with this particular proposition here. I can't remember the number of this one. I think it's one of the primitive propositions, I can't remember which number it is, but the principle of permutation with appropriate substitutions. So P has been substituted for not P, Q has been substituted for P, and that leads to this particular assertion. So effectively this is an instance of this proposition, this permutation, principle of permutation, and we call this 1. So far so good. Then we move on to the second line. Now in our little square box here we've got a bit more information now, because things are starting to get more complicated. We need a few more hints maybe as to where things have come from, where things are going. So what we can see in here is that whatever we're doing has something to do with what's happened on the first line. So what's happened on the first line is coming into what's happening now on this line. Also, whatever's happening, we're going to be making some kind of inference using our rule of inference 1.11. And then we've got the star 2.1. So what this means altogether is that the rule of inference 1.11 is being applied to effectively this line 1 and the proposition star 2.1, but this just hasn't been written in the demonstration explicitly. It's kind of been left out. So in the last proposition that I proved, which was 2.05, if you remember, the second line was effectively just a statement of 2.06 actually, that I went through the demonstration, and there was just a statement of 2.05 on the second line without any alterations, no substitutions or anything. Well, it's kind of the same situation here. The star 2.1, I could include it as another line, but it would just be a statement of 2.1, whatever 2.1 is. Presumably it's something to do with this here. And indeed it is. So in here, I could have another line, which is something like star 2.1, which will allow me to assert that not P or P, which is very similar to this, by the way, the law of excluded middle, although it's not identical. And even though they're very similar, and you might argue, well, surely you can just flip these around. Yes, we can, and that's what we're doing here, but we've still got to go through the proof of that. And if I were to do that, so I'd still have the first line here, then the final line of the proof would be, or I'd call this 2 for a start, it would be 1, 2, and then an application of star 1.11, and I'd get my P or not P. So again, the rule of inference is being applied to an implication and which has a hypothesis and a consequence that has been asserted, and which is line 1, and then the hypothesis of that implication has also been asserted, which means that I can conclude the consequence of that implication through my rule of inference. So this would be a more complete version of this, but as we will see, we will try to find ways to shorten things as we go through the various proofs of Principia Mathematica. Okay, so the next proposition that I want to go through is 2.16, and there's quite a bit for me to go through here because there's a lot of new convenient notational principles that are going to be introduced all in one go effectively, but they are essential, as hopefully the explanation will clarify. So 2.16 states that it can be asserted that P implies Q implies not Q implies not P. So this is your typical the principle behind, for example, proof by contrapositive. If you want to prove that P implies Q, then you assume you show that not Q implies not P. Okay, we don't have an equivalence here, we've got an implication. Ideally this would be an equivalence, and it wouldn't be too difficult for us to prove it in the other direction as well. Prove that this implies that not Q implies not P implies P implies Q, and then that would establish an equivalence, but we don't actually have a notion of equivalence yet. So we're going to have to prove them separately, keep them separate until we get onto chapter 4, section 4, when the idea of equivalence, logical equivalence, is going to be introduced. So we've got two demonstrations here. This one, which is the demonstration as it appears in Principia Mathematica, and then we've got this demonstration here, which is my version, which is a more complete version. I'm not saying, by the way, that this is what should be in the book. No, this is absolutely what should be in the book, in my opinion. But there is a point that I want to make by comparing this to this. So there are certain notational aspects here that really need to be explained through reference to a more complete demonstration version of the demonstration. Even so, even though this is a more complete version, I've still had to take a couple of little shortcuts here, just because I didn't have enough space on the board to fit it all on. But it's not too serious. Okay, so again, just to clarify the dot notation here, this single dot here brackets off the P implies Q. This single dot brackets off the not Q implies not P, and then the double dots here brackets off the whole of the expression. So let's have a look at the first line of the demonstration. So it says, according to star 2.12, that it can be asserted that Q implies not Q. So star 2.12 is the proves that P implies not P. And there's also, I think it's either the one previous, or maybe 2.11 or 2.13, where we get not P implies P. So we would have enough there for an equivalence, but again, we don't have a notion of equivalence, we don't have it defined yet, so we're going to have to keep them separate just for the time being. So with an appropriate substitution, presumably Q substituted for P, then we get Q implies not Q. But now something strange happens. We've got an implication symbol. This is not something that I've incorrectly written on the board. This belongs here and it means something, but it doesn't seem to point to anything. Well, it does. What it implies is this thing here, that this can be asserted. So this can be asserted implies that this can be asserted. So this is different to a normal implication where we've got hypothesis and consequent. When we've got P implies Q, that doesn't mean that we can assert Q. But here we've somehow got that this implies that this can be asserted implies that this can be asserted, and this is a shorthand notation. So if we think about our rule of inference, which goes something like, if P can be asserted and P implies Q can be asserted, then Q can be asserted. Well, this is a bit of a pain to write out. Not so much of a problem when we've got individual propositions, but when we've got propositional functions involved, which is what we've got here, things can get out of hand very quickly. That's what's going on over here. Because I've written everything else in full. So what we do is, instead of writing this, we just write P implies Q can be asserted. So in other words, Q follows from P. But there's something that's not being that is not explicitly stated in this notation, and that is this implication here. But it is implicit in the notation that we use. We understand this to be a shorthand notation for this. So in other words, if I were to write out these first two lines in full, I would get something that looks very different. So I'd get the first line, which would be Q implies not Q. The second line, which here 2.05 is referenced as the proposition that's being used for this. But if you check this against 2.05, it doesn't match. It doesn't match because this is only the consequence of 2.05. The hypothesis has been stripped away, and the hypothesis is this thing here. So it would be, I better get this right, Q implies not Q, implies P implies Q, implies P implies not Q. In fact, it's exactly the line that I've written here in this more complete demonstration. So then, because I've got the main implication here is this, and the other implications are kind of subordinate implications, the hypothesis is Q implies not Q. Well, that's this what I've got here. So I've got the hypothesis asserted. So that means then that according to my rule of inference, I can go straight to the consequence of the main implication here, which is that thing. So I've dropped the hypothesis and I've just gone to the consequence. So the 2.05 here, this is what I've said a couple of times, that this only gives a hint. What is in these boxes is only a hint as to where things have come from and where they're going. Some of the finer details you've got to figure out yourself. So this is not merely a statement of 2.05, it's just the consequence of 2.05 with the hypothesis already dropped. So think of this line here as a single line effectively saying something like this. So let's just have a look at the third line of this now, which is it's just a straightforward application of 2.03 with simply Q replaced with not Q. There's nothing really for me to say about this. It's exactly the kind of thing that we've seen already in previous demonstrations. We label this 2 because we're going to be using this in a second. So let's have a look now at this fourth line of this demonstration, because there's quite a bit for me to actually explain in this particular line. One of the first things that we might notice is that we've got something that's of a very similar kind of format to what we've seen previously on the first two lines of the demonstration, which is something like this, which you might read as P therefore Q, or Q follows from P. And when we use this up here, we understood this as being a shortcut really for an argument of this kind of form. So P is asserted, P implies Q is asserted, and then we can use our rule of inference 1.1 or 1.11 to make the to assert the conclusion down here. So this is understood as being shorthand notation for this here. So what we can gather from this then is that an assertion is being made, which happens to be what we're wanting to prove, by the way. An assertion is being made in light of what the lines that we've labelled 1 and 2 say. So how this exactly happens, not all of the details are necessarily included, but we might expect that it would be something along these kinds of lines. But the problem is, when we inspect the lines that we've labelled 1 and 2, they're not of the right form, because we might expect 1 and 2 would be of, 1 might be of this form, 2 might be of this form, and then we can make the assertion. But that's not the case. What we've got instead is that line 1 is of the form A implies B, and line 2 is of the form B implies C. And notice that the consequence of this implication here is the same as the hypothesis of this implication here. And from these, evidently, we've asserted that effectively A implies C. But this is not an inference of the type that we'd expect from either an application of either 1.1 or 1.11, and it is in fact a different type of inference called a syllogism. Notice the syll written here, which indicates that either proposition 2.05 or 2.06 has been used to make this particular inference, and it's not just the basic rule of inference 1.11 or 1.1. In fact, in this particular case, it's 2.06 that's been used. But here's the problem. How do we know that we can actually use the rules 2.05 and 2.06 as rules of inference? Because this surely can't be taken for granted. At the moment, we've only got our basic rules of inference. What we need to show then is that it's actually possible to reach the same conclusion, using our basic rules of inference, but then somehow out of this we can show that we can form some kind of derivative rule of inference, some less fundamental but maybe more useful rule of inference, and that's where the syllogism is going to come in, because really at this stage we only know how to introduce propositions, whether they're primitive or otherwise, as premises in our demonstrations, and not how to use them as rules of inference. There's nothing saying at this stage, nothing telling us that 2.05 or 2.06 are rules of inference or how they should be used as rules of inference. They are, as far as we're concerned, just propositions like any others. Notice that in this version, the syllogism, as it's being used as a rule of inference, doesn't appear as a premise in the demonstration. And strictly speaking, we don't know how to do that yet. We only know how to introduce the syllogism as a premise. And this is an interesting feature of rules of inference. A rule of inference, when being used as a rule of inference, doesn't actually appear as a premise in our reasoning. It's almost like the rule of inference, it kind of hovers outside the demonstration somewhere, just waiting for an appropriate chain of premises, an appropriate sequence of premises to appear, and then it acts and it makes its inference without actually entering into the demonstration itself. Having said that, there's no reason why a rule of inference can't be introduced as a premise into our reasoning. After all, even though we've not established the syllogism as a rule of inference yet, we only have it as a proposition. The fact is that it is a proposition in its own right, and it can be asserted and it can be introduced as a premise into our reasoning. But if we do that, then either we're going to need to use a different rule of inference to deal with this new premise that we've introduced, or if we've already established that this this particular proposition, say 2.06, has this double use, that it can be used as a rule of inference or as a premise, then it might be that we can still use the syllogism, a separate instance effectively of the syllogism, as a rule of inference, and apply it to the instance of the syllogism as a premise. There's nothing preventing us from doing that, and it's not circular or anything to do that, provided that we've already established that the syllogism can be used in both ways. So it's almost like there's two separate instances of the syllogism, both in the same demonstration but performing different roles. So what we'll have to show is that we can actually reach the same conclusion by introducing the syllogism as a premise and then using our basic rules of inference only. And that's what's happening in this fuller demonstration over here. Notice that lines 1 and 2, so that line 1 here appears here as line D, and line 2 appears here as line F. But I've got to deal with them separately. What I've got to do, rather than making the inference directly from A implies B, B implies C, therefore A implies C, which is the more efficient way to go about things, what I've got to do is I've got to introduce this new, I've got to have this line in here, which has been formed from 2.06. So this line here comes from 2.06. 2.06 introduced as a premise now, not being used as a rule of inference, it's being introduced as a premise, and I've been able to drop the hypothesis of 2.06, which is P implies Q implies P implies not Q, because that was asserted here in line D. So I can drop that and I get this line here, of which this is the hypothesis of this line, of this assertion here. So using my basic rule of inference, 1.11, then I can drop the hypothesis, because both the implication and the hypothesis are asserted, so therefore I can assert the consequent of the implication. So what we've shown here is, at least in this particular case, that even though we've got premises of the form A implies B and B implies C, that we can, if we treat them in the correct way, we can use our basic rules of inference on these, if we bring them into the right form, and make the conclusion that we want to make. But it's a very inefficient way of going about it. So what we effectively do is we say, right, rather than going through all of this, we're just going to start to apply the syllogism directly as a rule of inference, on the understanding that if we were challenged about this, about what justifies using the syllogism as a rule of inference, we can always point to this kind of argument. We can always say, well, when we use the syllogism as a rule of inference, in effect, this is what we really mean. And then this is unobjectionable, really, because we're just using our basic rules of inference. So what we're looking at here, when we use a syllogism to make an inference, is we've got something like A implies B is asserted, and B implies C, and then using the syllogism we can assert that A implies C, for instance. And we can also extend this to longer chains if we want to. So we might have not only A implies B, B implies C, but we might also have C implies D. Let's number these 1, 2 and 3. Then the next line in the reasoning here would look something like this. So we'd have the syll there, 1, 2, 3 implies A implies D. Okay, and we can extend this indefinitely, so it's not difficult to imagine how this is going to be extended. Also, another little shortcut that we're going to see in Principia Mathematica is, rather than writing out the actual statement here that we wanted to prove in full, because these are going to get quite lengthy, some of these statements in here. What we're going to use is a little abbreviation, which is just simply the word prop. So when we see something like that, assertion symbol followed by prop, that means effectively that what belongs in here is the statements, the proposition that we originally wanted to prove. So this acts as a kind of QED, or if you look in some maths books, at the end of a proof there might be a little square or something like that. This is acting as the same kind of thing. So what we're going to do now is we're going to look at how we can show that the rule of this syllogism can be used as a rule of inference in general, because we've shown it here effectively in a particular case that it works here. But this might just be a fluke, so we just need to go through the argument in a bit more detail, in a bit more generality, and just to be sure that it is valid, that whenever we see chains of implications of this kind of form, that we can always apply this syllogism as a rule of inference. Okay, so this goes through the steps that we need to go through to show that syllogism works in general, really, as a rule of inference. So what we've done here is we've introduced the syllogism, in this case 2.06, as a premise, and somehow we can assert how this comes about is going to vary from one problem to another, from one proposition to another, but we somehow managed to assert that A implies B. Therefore we can use our basic rule of inference to drop the hypothesis here and just end up with the consequent of the main implication here, which is this. And then again, somehow we managed to show that B implies C, which allows us then to use our basic rule of inference to assert the consequent of this particular implication here. So what we end up with is this A implies C. So what we can shorten this to thinking, to imagining this as being like, is if we see the sequence of premises A implies B and B implies C, that even though we don't need to, we can, if we want to, go through all of this to get A implies C, or we can just think about it as a direct application of the syllogism as a rule of inference. So when we apply the rule of this syllogism as a rule of inference, when we see these two assertions here, A implies B and B implies C, then even though we might not consciously think about it, we understand that in the background this is the kind of thing that's kind of going on. So this argument here. And then we can continue this process because we might have longer chains of reasoning as we go along. So we can go through the whole thing more or less again and get to A implies D. And then we could go through it again to get to A implies E, A implies F, and however far along we need. So we can have chains of implications of indefinite length, although not infinite, any finite length, and we just keep going through this process. And that's the idea behind showing that the syllogism can be interpreted and used as a rule of inference. So now we're going to get really lazy with our notation, and this is something that's through necessity more than anything. So it's not laziness for the sake of laziness, it's laziness for the sake of necessity, really. It's just using more convenient notation, shorter notation to explain, to notate the ideas, the steps in our demonstrations, for instance. Because what we've got here with our syllogistic inferences is a chain of implications of this kind of form. B implies C and C implies D, and then from these we would conclude, so 1, 2, 3, so we'd say syll 1, 2, 3 assertion, oh goodness, A implies D, for instance. But bear in mind that our propositions are going to be getting longer and longer and longer as things go on, potentially, and more complicated. This seems a bit of a hassle, to be honest with you. So we're not actually, sometimes we will still do this. So I'm not saying that this notation is going to disappear entirely, but what we might see happening, in fact we will see happening, is that things will be shortened somewhat. So we won't write this in. Let's get rid of those. These are going to disappear here. And put some little dots in here. So we're going to see something like this instead. So what was written previous, what I've just rubbed off effectively, is going to be in some cases replaced by this. And what we might see in here also are little square boxes which indicate how these implications are actually coming about. So there's going to be some things written in here, our usual hints as to how things have come about here. Again, the hints might be quite detailed in some cases, other times they might be quite meagre in many respects. Okay, so now it depends what we're going to be doing with this as to how we finish things off with it. Because it might be that this is just a part of, effectively a part of our demonstration, but it doesn't actually take us to the end of the demonstration. In which case we might label this 1 here. And then what that 1 means is it indicates that this is all one line. So effectively A implies D. So 1 indicates this thing here. On the other hand, let's say, let me just rewrite this. Let's say we actually want to finish our demonstration here. Well, in that case then we'll have a tendency to write our prop there, and that will indicate that our demonstration is finished, that we've proved what we needed to prove effectively. The syllogism is probably the most important rule of inference that we're actually going to be using from now on, really. That's not to say that we won't use our original rules of inference, but the syllogism will start to take over as the dominant rule of inference. And if we think about it, it is probably one of the most used types of inference. If we think about a mathematical proof, for example, then we start with our premises and we've got the thing that we want to prove. And how do we get from start to finish? Well, we take a sequence of steps, and we can visualize each sequence of each step as effectively an implication, or at least the transition from one step to the next as an implication. So what we have is a chain of implications. A implies B, B implies C, C implies D. And what the syllogism allows us to do then is to stick all of these together in a kind of a logical product. A implies B and B implies C and C implies D. And then if A is our premises that we start with, and D is our the thing that we're actually wanting to prove, then we've got that A implies D. We can use a syllogism, a syllogistic inference, to infer that A implies D, and that can be asserted. And because we also know that our premises at A are true, or at least if we know that they're true, then they can be asserted, and therefore we can drop the premises and go to the conclusion. So in a way, a mathematical proof is a very good example of what we might consider a kind of syllogistic chain of syllogistic inference, chain of implications leading to a natural syllogistic inference. Even though probably as you go through a mathematical proof, I certainly don't necessarily think of it that way. That's probably one way that we can interpret it. Also, something that I meant to mention when it comes to notation such as this, which is our indication that an inference has been made, at least in some context. This might be written in various different ways. So it won't necessarily be written all on one line. Sometimes we'll see it written as this, so across two lines. Sometimes it might be written as this, again, across two lines, but instead of the implication symbol being here, it's up here. So be prepared for this if you are reading through Principia Mathematica. These all mean the same thing. And also we can extend this even further. If we've got longer chains of inferences, we could end up with another one in here, say R. So we've got three. P therefore Q, and Q therefore R. Or P therefore Q therefore R, however you want to say it. And we can extend the chains as long as we need to any finite length effectively. So let's just have a look at proposition 2.31 now. There's nothing particularly special about this proposition. I've really just decided to include it because it gives a good example of the notation that we've just introduced. So the proposition is effectively commutativity of disjunction, obviously with elementary propositions. We did introduce in the primitive propositions a form of commutativity, but it was different to this version of commutativity here. Kind of works in the way that we would expect commutativity to work. So if we've got in algebra A times B times C, this would be equal to A times B times C, for instance. And there would be no change of order of the A, B and C. It'd just be the positioning of the brackets that would change, grouping together the AB here and the BC here. So this works in a much more analogous way, whereas the primitive proposition that was introduced was still called commutativity, but it worked in a slightly different way to what we might expect when it comes to algebra, because there was a bit of a change around of the order of the letters. The reason given for that was that it had more, the version given in the primitive propositions has more direct deductive power than this one does. Not verified that myself, but I'm taking Whitehead and Russell's word for that. But this is the one that works more in line with what we'd expect from an algebraic perspective. Inexplicably, there is a use of brackets here, and actually in a couple of propositions. I don't know why brackets are used, but just so that you're aware, this proposition could be written out using purely dot notation, which would look something like this. So this is the version that's given in Principia Mathematica. This is my version that I've just given using purely dot notation. But they mean exactly the same thing. And then we get into the demonstration. Nothing really special about the first line of the demonstration. It's just an assertion made using proposition 2.3. Whether there's any changes in there, any substitutions, I don't know, but I don't think so. It's not important anyway. But then we see the chain of implications appearing, which is indicating that we're using this syllogistic inference at each stage, even though we don't actually bother writing it now. We've got really lazy and we've not even bothered writing the syllogism in there. It's just understood the format, the way that this is presented is indicating that it's really a syllogism that we're using. So it's effectively like this would be written here, it's just we couldn't be bothered to write it, and then this would be written here, but we just couldn't be bothered to write it. So we get the chain of implications. Then we get the prop at the end, which indicates that what we wanted to prove has been proved. Notice that the prop effectively is talking about this whole thing here. So that's effectively our proposition, what we wanted to prove, which is exactly what we needed up here. In the square brackets, we've got the information that tells us how these implications have been made, how we've got this particular line. As we progress through, the information contained in these boxes has to be kept in check, really. So the main propositions used to make an implication will be mentioned, but then other ones will just not be mentioned. In the same way that we've actually stopped mentioning really the rules of inference that we're using. To a certain extent, it doesn't make too much of a difference which rule of inference is being used, as long as it's correct, really. Just sticking with that theme of not really distinguishing between different types of inference, what we're going to find as we go through is that not only do we not distinguish between different types of inference, but we're going to fail to distinguish between a proposition being used as a rule of inference and a proposition being used as a premise. This was important in the early stages for us to make this distinction, to make it quite rigidly and quite strictly. But as we go forward, sometimes usually it's not really going to make a difference. It's going to be clear from the context whether a proposition is being used as a rule of inference or whether it's being used as a premise. So we don't really need to distinguish quite so strictly. So what we're going to see is, and if I take the last line of the demonstration of 2.16 as an example here. So we saw there something like this. So we had Syll, and then 1, 2, implication symbol, prop. So we had something like that. Well, what we're going to see now is that rather than mentioning the Syll outside here, where it's kind of suggesting we're using it as a rule of inference, we're going to start writing something like this. 1, 2, so we're still using 1 and 2, and then we write Syll there, and prop. So what this would suggest at first sight is that Syll is somehow being used alongside 1 and 2 as a premise. So we've got premise 1, premise 2, premise, which is the syllogism, and from these somehow we're making the inference which takes us to the proposition. But that might be the case in some instances. But even if we use Syll as a rule of inference, rather than mentioning it in square brackets over to the left hand side here, we might actually include it in with the premises. So the true premises might just be 1 and 2, and then this is actually the rule of inference that's being used. Why this is, I've no idea necessarily, but that's how things are going to work. But like I say, sometimes we won't distinguish between a proposition being used as a proposition, as a premise, or a rule of inference. Sometimes we won't distinguish between this or that rule of inference. Sometimes we will mention the rule of inference, sometimes we won't. In a way, it's kind of haphazard, but the context should clarify things. If you're familiar enough, if you've spent enough time in these early stages getting familiar with the notation and how it works, then it should really be fairly clear from the context what's going on. Even though if you are unfamiliar, if you're trying to stick rigidly to the rules that have been introduced too rigidly, then you might misinterpret things further down the line. So you do have to be a little bit relaxed. So I have spent quite a lot of time going through the notation in this video because it is important to do so, to understand the notation and be able to use it strictly and rigidly if need be. But at the same time, you've got to be quite flexible as well with your notation and how you interpret the notation as well. So just a few closing words on section 2, which is what we're practically finished with now. The reason I've spent so much time on section 2 is not because of its incredible importance in Principia Mathematica, don't get me wrong, it is important, but really it was to just clarify all of the notation and the style of presentation and things like that, and how to interpret the demonstrations properly. There are still a few little things regarding the notation, a few little quirks, minor quirks here and there that I've not really mentioned, but I don't really want to spend any more time on section 2. I'm really wanting to move on now. Towards the end of section 2, there's just a bunch of propositions, miscellaneous propositions, that are fairly straightforward to prove. They're just stated, there's no demonstrations given, although in the actual book you are directed towards which propositions are going to be useful in the demonstrations of these propositions. It is worth maybe going through a few of them yourself just to make sure that you've got a good grasp of the notation, but there's no real need to go through every single one of them. The fact is that probably most of the propositions are not going to be used very much as we go on. which makes them not terribly important, but you're likely just to forget them anyway, a lot of the propositions. So don't worry if you don't remember all of the propositions going forward. If you do, then you've got a better memory than I do, but I certainly don't remember all of them. Moving on to sections 3, 4 and 5, I should only really need to spend a few minutes on each of these now. Like I said, the reason I spent so much time on section 2, a disproportionate amount of time on section 2, was just because to establish all of the notation. We've just got a few definitions to go through from section 3, 4 and 5. There's a couple of propositions that I want to highlight, but other than that, there's nothing really that I want to spend any time on or dwell on to any great length. So, kicking off with section 3 then, we've got the definition of the logical product. P.Q, which is read P and Q, is defined in terms of negation and disjunction of P and Q, and it's not P or not Q. Okay, so whenever we see this collection of symbols here, we are free to replace it with just simply P.Q. Definition 3.02, it's kind of a chain of implications. P implies Q implies R. We're to interpret this as meaning P implies Q and Q implies R. We've kind of already seen this notation in a way in section 2 when we had the things like A implies B implies C implies D. I guess you could interpret this as being something like A implies B implies C implies D if you really wanted to, and then you can see it as a logical product of the individual implications. A implies B and B implies C and C implies D. You're fairly unlikely actually to see this as it's written here. I can't recall any instances where I've actually seen this in Principia Mathematica, and it's really struck me. What you're more likely to see is this, to be honest with you, which in a way makes the definition a bit even more superfluous than it already is. Considering that definitions are fairly superfluous from a theoretical standpoint in the first place. 3.03 is the first actual proposition in section 3, and it says that given two asserted propositional functions, phi p and psi p, whose arguments are elementary propositions, we can assert the logical product of phi p and psi p. So what this is an extension of the primitive proposition 1.72, which is the axiom of identification of real variables, whereas in 1.72, when we've got the two asserted propositional functions whose arguments are elementary propositions, we can assert their disjunction. Now we can assert their logical products. We can only do that now because we've got this here. It turns out that this is going to be more useful to us. This is actually proved. There's a demonstration of this, and this extension to 1.72 is probably going to be more useful to us. We tend to come across logical products much more than we do disjunctions, although obviously we do come across disjunctions as well. The fact that both of these functions have arguments, elementary propositions, ensures that they're of the same type, so we don't need to worry about them being of different types. If they were of different types, we wouldn't be able to assert this. We can't assert the logical product of two propositional functions whose arguments are of different types. We can't do it. 3.33 and 3.34, these are more convenient versions of the syllogism. So this is kind of like 2.06, and this is more like 2.05, I guess. These are going to be much more convenient to us. The ones that we introduced in section 2 were a little bit cumbersome. That's the best we could do at the time because we didn't have the notion of logical products in section 2. But these turn out to be much more convenient forms. So when we use the syllogism going forward, really it's probably going to be these ones that we've got in mind that we're using. Although it's not to rule out the use of 2.05 and 2.06 as well. There are a couple of minor errors that I've spotted in the book on this section 3, which I'll just mention now. So I'm not making any claims to have gone through everything line by line and identified every single error. These are just two things that I noticed as I was going through. So the first one is in the demonstration of 3.03. Okay, so let me write it down. So what we see in the book is we see something like this. This is just one of the lines of the demonstration, so I'm not writing the whole thing down. 3.03 and then there's some proposition after that. Okay, so the error here is this thing. This should be not 3.03 but 3.01, star 3.01. And there's two ways that I know it can't be 3.03 for certain, and that's because one, we're trying to prove 3.03 here. So to use 3.03 to prove 3.03 would be circular, but also the fact that there are brackets surrounding the 3.03 would indicate that it's a definition. Well, 3.03 is not a definition. It's an actual proposition with its demonstration, and it's not a primitive proposition. It's not a definition. So this is in error, and it should be star 3.01, which is use of this definition here. So it's just a minor error. And then there is another one in 3.47. So again, I'm just going to write out the part of the proposition where it occurs. So we've got, this is towards the end of the proposition, 3.03 star 2.83, and then there's another assertion, and it continues there. And there is an error here, which is this use of 2.83. 2.83 does not need to be used in this. It should be actually star 3.43 and 33, which seems quite unusual. It does seem at first quite unusual that they've misprinted this or whatever as 2.83, but there are reasons for this, I think. The reason that they've quoted 2.83 is because the next proposition has a very similar string of symbols here. It's got the 1, the 2, and it uses 2.83, but that is a correct use of 2.83, so maybe it's just got kind of mixed up along the way somewhere. But also, how do I know that it's 3.43 and 33? Well, actually it tells us. If we turn back a couple of pages, there's an introduction to the chapter, and it gives a bit of a commentary on the demonstration of 3.47, fortunately, and it says that it's 3.43 and 3.33 that I used. It doesn't say that there is an error in the book, but that's the conclusion that we can draw, I guess, from that. So they're the couple of errors that I've identified. So that really brings us to the end of section 3. In section 3, they're really just really simple propositions, the kind of things that you'd expect involving logical product in any textbook on symbolic logic. So I'm not really going to spend any time going through it. I'm going to move on quickly now to section 4 and then section 5. So let's have a look now at section 4. As with section 3, I'm going to fly through this relatively quickly, just picking out the main features really of the section. The propositions that are contained in this section are really, just like section 3, the kinds of things that you would expect to see in any kind of basic, elementary, introductory textbook on symbolic logic. So I think anybody reading through this section on their own will be able to manage quite easily. So the first thing that we start off with is the definition of equivalence of propositions. P and Q propositions are equivalent. P is equivalent to Q, is defined to be the logical product of the two implications, P implies Q and Q implies P. Okay, so what I'm just going to talk about for a few seconds is how to interpret, in a more kind of intuitive sense, what's going on here. So we've got the symbolic definition, the symbolic interpretation. We can interpret this symbol in terms of this collection of symbols here. But intuitively, what do we mean when we say that two propositions are equivalent? Well, we're certainly not saying that they are identical. We're not saying that they are effectively one and the same proposition. So we're not saying that P and Q are the same proposition. We've got no need really for such a notion. We're not really interested in a proposition being equal and identical to itself necessarily. It's not of much use to us. So we don't really have a use for a symbol such as P equals Q. If I were to interpret this is not defined, by the way, but if I were to interpret this, I would take this as meaning effectively that P and Q are one and the same proposition, that they are just two instances of one and the same proposition. But that's not what we're saying. Equivalence is a slightly weaker notion, I guess, than identity or equality. We will introduce the equals sign in a different context in a few chapters, but we don't use it in the context of propositions or propositional functions. Equivalence, so what we're saying when we say that P and Q are equivalent is that there is some feature that they have in common. And the feature that we pick on is their truth value. So when we say that P and Q are equivalent, we say that we're basically saying that they are both either true or they are both false. So if P is true, then Q is true. If P is false, then Q is false. So they've got the same truth value in that respect. And that is what we mean when we say that P and Q are equivalent propositions. So we're certainly not saying that they're identical. It's just some particular feature that they have, which is their truth value. And whether that's a feature that they possess objectively, completely separate thing, but we just assume that a proposition has a truth value in some respect. Okay, so why is that useful to us? It's useful because the types of propositional functions that we're interested in are truth functions. So we don't deal with propositional functions that are not truth functions. So a truth function, a propositional function that is a truth function, let's say f of p, where p is a proposition. This is a truth function if the function itself, the value of the function, only depends on the truth value of the proposition in here. So therefore, if I know that p is equivalent to q, then they've got the same truth value. So that means wherever I see p, I can replace it with q. And if I've got a truth function, if f is a truth function, then f of p will be equivalent to f of q. Remember, if this is a propositional function, then with fixed values of p and q and everything, then these will become propositions themselves. So this symbol makes sense between these two functions here. So how might this kind of break down? Well, it wouldn't work if I made this substitution if f is not a truth function. So an example of a truth function might be something like x believes p, where x is a person. Because people being people, they believe some true things, but they disbelieve some true things. And they correctly disbelieve some false things, but they incorrectly believe some false things. So it might be that I take the two propositions, which don't necessarily have anything to do with each other, which are cats are mammals and frogs are amphibians. So these two propositions are equivalent by virtue of the fact that they have the same truth value. Cats are mammals, frogs are amphibians. They've got the same truth value, they are equivalent. Whereas it might be that I believe correctly that cats are mammals, but I disbelieve that frogs are amphibians for whatever reason. Maybe I'm not very educated. So that means that this x believes p is not a truth. It's not a truth function. It's still a propositional function, but it's not a truth function. It doesn't have the same kind of objective feel. that a truth function does. So that's why we're more interested in truth functions, because they've got a certain objectivity that non-truth functions don't have. We get all sorts of problems coming in if we start to deal with functions that are not truth functions. We get all kinds of problems coming up that we don't really want to have to deal with, certainly not at this stage. So now let's have a look at the second definition, which is just P is equivalent to Q is equivalent to R, all one symbol effectively, is interpreted as being the logical product of these two equivalences. P is equivalent to Q, Q is equivalent to R. And then we've got these three propositions here, 4.2, 4.21 and 4.22. What these show is that equivalence of propositions have the property of being reflexive, symmetric and transitive, which are particularly nice properties. I guess in modern terminology that would mean that this symbol is an equivalence relation, although we don't necessarily have that notion at this as we're going through Principia Mathematica, but we do have the notions of reflexivity, symmetrical and transitivity. And then, okay, let's get rid of this. I've written down proposition 4.5, and the demonstration of this is actually omitted from Principia Mathematica, but I've written it out for a particular reason. And that's because if you recognise this is effectively, in a way, the definition of logical products that we saw from section 3. P.Q is defined to be not P or not Q. However, the problem was when we introduced the definition in section 3, it's introduced as a definition. It's not introduced as an equivalence. So sometimes I want to be able to assert a definition, but I can't. I can't just assert this as it is here, necessarily. Because this symbol doesn't exist in our system. Remember, this definitions are effectively theoretically superfluous aspects of our theory. They're practically very useful, theoretically superfluous. I've got this symbol. This symbol doesn't exist in my system. This is just something that exists as a convenient symbol for me to abbreviate things that I've agreed to use. We've agreed to use amongst ourselves, but it's not really a formal part of our system. So if I were to assert this, it wouldn't make any sense. If I want to assert something like this, I'm going to have to think, what am I going to replace this symbol with? And that really depends on the kinds of things that I've got involved. So here I've got effectively propositions. This is a proposition, this is a proposition. So really I need an equivalence symbol between you. Remember, we don't use equality. I can't just get rid of the df on the end there and just say this is equal to this and assert that instead, because we don't have a notion of equality of propositions. And we could argue, well, this proposition is definitely not equal to this. It's not identical, because this is saying something very different to this in many ways. So I've got to think, how can I get an equivalence symbol in here? Because that is the symbol that I'd really like to have. And that's what happens here. So we can use this proposition 4.2 quite effectively to turn definitions that involve elementary proposition or propositional functions. We can take the definitions and we can convert them into equivalences using 4.2. Because what we do is we apply 4.2 to us, in this case assert P.Q is equivalent to P.Q, because this says that P is equivalent to P. So I just replace the P with P.Q, and then I apply definition 3.01 to the right hand side of this, and I come out with the proposition that I want proved, bearing in mind that all of this I read as a single line. All of that, and that's the proposition that I wanted to prove. And I can do this for any definition involving elementary propositions. So I could have done this for the definition for implication, for instance. same sequence of steps basically. You start 4.2 to make a particular assertion of a proposition is equivalent to itself, and then replace one side with the appropriate definition. And so let's say I had P implies Q is equivalent to P implies Q here, then one of the sides I just replace with the definition from 1.01, and I get P implies Q is equivalent to whatever the definition is, not P or Q, for instance. So I can turn any definition that involves propositions into an actual proposition itself, because this is not a proposition. Notice there's no assertion symbol here. Definition is a very different thing to an assertion. So here we are, the very last section of this video at least, which is section 5. This should really only take a couple of minutes tops. This section in Principia Mathematica is just a mishmash of leftover propositions that in some cases would fit better in some of the earlier sections, but it's just that maybe we didn't at that point have the right propositions in place in order to prove them, so they've just had to be left until this chapter. So this is kind of tying up some loose ends in this chapter. Again, I'm not really going to go into detail with the specific propositions. They're completely unexpected. There's in many ways there's nothing out of the ordinary with these propositions. I've just chosen one particular proposition because it's an example of a new little bit of notation that we will see quite consistently as we go forward. So there's nothing particularly important about this proposition, but just so that you know, it says Q implies not R implies P or Q and R is equivalent to P and R. And just so that we know how the brackets are working here, I'll just write it out again. Q not R. P dot R. Okay. So this here and this here are logical products. All of the rest are brackets. So we've got a dot here representing a bracket. I've got to start somewhere, so I may as well start there. And it passes over the logical product because this doesn't represent a bracket. And it goes as far as the two dots here, which also represent a bracket. This dot, open brackets there, continues to the end of the expression, at which case I've got to close the brackets. The two dots here bracket off all of this section. The single bracket here brackets off that part, and then the three dots here bracket off the whole thing. So I get something like that. So the bit of notation that I really want to comment on is just this use of HP here, which means hypothesis. So the hypothesis, when we see this HP, usually that will refer to black pen. It will be referring to this part of the proposition that we're actually wanting to prove. Okay, so the reason for this is because sometimes the hypothesis can be quite long, can be quite a lengthy expression, and this just shortens things down a little bit. So it's understood that the HP here is referring to the hypothesis of the main implication in the statement that we're wanting to prove. And there are slight variations on this because sometimes we might want to refer to the hypothesis of something in a previous line. So if we've got a line labelled 1, for instance, we might use the symbol HP with a 1 after it like that. Or if it's the hypothesis of the line that we've labelled 2, similarly we get something like that. But HP on itself, by itself, on its own, is going to refer to the hypothesis of the main implication of the assertion that we're actually trying to prove. Also notice here there's quite an absence of the square brackets, and this is going to be something that's quite common going forward as well, that we will not usually see square brackets. We will sometimes, but not very often, see square brackets in front of an assertion symbol. We'll still see the square brackets in relation to something like this, where we've got, this is the syllogism that we looked at earlier, We'll still have the square brackets to sometimes tell us where and how this has come about, where it's come from and how it's come about. But usually the square brackets that would be placed before, would have previously been placed before the assertion symbol, will actually start to do something like this now and work their way in front of the assertion symbol. So previously this would have been written maybe something more like star 4.4 assertion P or Q dot R blah 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 blah. It would have been written something like this, but now it will tend to be written more commonly like this. Now I interpret it as meaning more or less the same thing. I don't really make too much of a sharp distinction between the two, but just so that you're aware, that will happen. And also, I copied this from the book, but I can't remember if there was anything written here in square brackets. I don't think so, otherwise I probably would have written it. But this is also quite a normal thing anyway, that sometimes you will get lines, there's implications, inferences, assertions made, and there's actually no reference telling you how it's come about. And usually that's intended to mean that it's kind of obvious, or at least it's obvious enough for you to figure it out yourself to a certain extent. So that brings us to the end of this video. If you have managed to stay with it to this point, then thank you very much for watching and staying with me. It is important that I've gone through all of this stuff because there are a lot of ideas, there is a lot of notation that really needs explaining in order to fully understand what's coming up. I don't expect that I will be spending quite so long on the sections as we move forward, but we'll see how things go. But hopefully this will give a good foundation for understanding what's coming up. So I'm going to sign off there with this video. If you do have any questions about anything that I've mentioned in the video that I've not explained clearly or properly, then please let me know. Leave a comment in the comments section or get in touch with me and I'll be glad to help. But thank you for watching this video. In the next video I'm going to move on to sections 9, 10 and 11, and I'll look forward to seeing you in that video. Thank you.